This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Week 2, Lesson 7, the ventilation load. To keep indoor air healthy, we deliberately pull in outdoor air, and that air arrives hot and humid or cold and dry. It becomes a load on the coil. We'll frame ventilation against infiltration, run the outdoor air through the same 3 standard air factors, then mix it with return air to get the temperature the coil really sees, and show the two are one calculation. Concept 1. What ventilation air is. Ventilation is outdoor air you bring in on purpose, metered through the air handler to dilute contaminants and hold air quality. Infiltration, from Lesson 6, is the same outdoor air leaking in unintentionally through cracks. Different intent, identical physics. Both drag outdoor air across the indoor-outdoor difference, so both become a load through the same standard air factors, just apply to the outdoor air flow. How much ventilation you need comes from a code, Standard 62.1, not the handbook, so we take that flow as given and defer the rate to Week 6. Setup, the outdoor air load. Nothing new here. Take the 3 standard air factors and feed in the outdoor airflow as the airflow. Sensible is 1.1 times the flow times the outdoor minus indoor temperature difference. Latent is 4,840 times the flow times the moisture difference. Total is 4.5 times the flow times the enthalpy difference, or just sensible plus latent. Use the outdoor design conditions against the indoor set point. Concept 2. Mixed air. The unit rarely handles pure outdoor air. It blends the outdoor airflow with recirculated return air, and the coil sees that mixture. The mixed air temperature is a flow-weighted average of outdoor and return, as printed on the mixing page. In shorthand, the outdoor air fraction times the outdoor temperature plus the return fraction times the return temperature, where the 2 fractions add to 1. Humidity ratio mixes the very same way. Setup, the worked problem. A summer system brings in 1,000 CFM of outdoor air at the design condition and mixes it into a 5,000 CFM supply, with the space at 75. The outdoor air is 95 degrees, 20 above the space, and 0.007 of a pound per pound more humid. The outdoor air fraction is 1,000 over 5,000. Solve. The outdoor air load. Sensible is 22,000. Latent is 33,880. Add them for a total of 55,880. Notice the latent beats the sensible. Humid outdoor air is a low sensible heat ratio load. The enthalpy route would give the same total, with an enthalpy swing near 12.4. Solve. Mixed air, 2 viewpoints. Flow weight the streams. 0.2 times 95 plus 0.8 times 75 is 79. Mixing lifts the coil entering air 4 degrees above the space. Here's the payoff. Take the coil view, 1.1 times the full 5,000 times that 4-degree rise, 22,000. Take the outdoor air view, 1.1 times 1,000 times the 20-degree difference, also 22,000. Identical, because the total flow times the mixed air rise equals the outdoor flow times the full outdoor difference. The mixed air sensible is the outdoor air sensible. 1 physics, 2 viewpoints. Traps, 4 ways this bites. 1. Match each factor to its driving difference. 1.1 with temperature, 4,840 with moisture, 4.5 with enthalpy, never crossed. 2. The outdoor air load and the mixed air sensible are the same heat, so count ventilation once or you oversize the coil. 3. Ventilation is not infiltration. Same equations, but one is metered air you size, and the other is leakage you can't. 4. The required outdoor air rate comes from a code, not the handbook, so take it as given, and use 1.1, not 1.08. Quick recall. Ventilation is intentional outdoor air for air quality. Infiltration's physics, on purpose. Run the outdoor air flow through the same 3 factors. 1.1 times flow times temperature for sensible, 4,840 times flow times moisture for latent, 4.5 times flow times enthalpy for total. Mixed air is the flow-weighted blend of outdoor and return. And the identity, the mixed air sensible equals the outdoor air sensible. Add it once. The rate itself is a code number, given on the exam. Next, Lesson 8, Pipe and Duct Insulation Requirements. We turn to the distribution system, the Handbook's minimum insulation thickness table, the equivalent thickness equation, and the duct R value table. Insulation requirements, with the bare heat loss pointing back to cylindrical resistance in TFS Week 3. Everything's at PEPrepEngine.com. Cheat sheet, worked solution, and a quiz attached here.
The full study guide with every equation and common exam trap is free at PEPrepEngine.com, link in the description. Structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.